Okay, so let's see what we got. There was actually 102 points possible, but I took it out of 100 just to make my life easier. The first set of vocabulary questions look like this. I was after quantized is a word that describes value that can exist in one of several states, but never between the two consecutive states. And that was like the chemist on a ramp versus the chemist on stairs. Ground state is the lowest allowed energy state for an atom. For C, I was after electron cloud or orbital is the region of space where there's a high probability of finding electron. Nucleus is the center of an atom. Of course, the nucleus of an atom holds the protons and the neutrons. I was after excited state, E, for an energy state that's above the ground state. Valence electrons are those outermost electrons of an atom. We're going to actually pick up here with you probably already know this, when atoms join together to make compounds or join together in a chemical bond, it's those valence electrons that make that happen. I was after mass number as the sum of the number of protons and neutrons of an atom. For the units that associated with atomic weight or average atomic weight, that's atomic mass units. AMUs are the symbol U. Isotopes are atoms of the same element with different masses because they have different number of neutrons in their nuclei. For J, I was after rare gas configuration as the phrase that describes that kind of complete octet, that NS2-NP6 rare gas configuration. It's the group 8A elements. So for here, these were each worth 1 point apiece. How many orbitals will be found in a D subshell? So a D subshell has 5 orbitals. An S has 1, a P has 3, a D has 5, and an F has 7. For B, how many orbitals would be found when N is equal to 3 at the third energy level? So we have a 3S, a 3P, and a 3D, and if you add up 1 plus 3 plus 5, you get 9. Another way to do that, I think I might have said in lecture, is you take 3 raised to the second power. That will also be how many orbitals you have. 3 squared is 9 also. At the energy level, N is equal to 3. C, what's the maximum number of electrons? We even did this in review. The maximum number of electrons that can occupy a p orbital. Any orbital, whether it's a p orbital, remember orbitals are boxes, can only accommodate 2 electrons. So the answer there was 2. Question D, what's the lowest value of N that can have the F subshell, and that's N is equal to 4. Actually, I verified this because later on you draw your arrow diagram and you pick up the F-type subshell at N is equal to 4. For E, what shape of an orbital is spherical? That would be an S-type orbital. So for question 3, where 6 points, you actually could go ahead and on the periodic table look up potassium, see what the average atomic weight is. It's the decimal number for potassium is 39.10. And then the way we get to it is this, where we take the weight of the isotope times its fractional abundance. But its fractional abundance is the percent abundance divided by 100. And then we add that to the next isotope, how much it weighs, and its fractional abundance, plus the third isotope, how much it weighs, times its fractional abundance. So down here, I'll just kind of let you kind of check how that worked. So 4, I gave you the symbol and asked for the name of the element, and for 5, I gave you the name of the element and asked for the symbol. Now, if you're a little bit hesitant on this, you need to keep working on this. This class is very accumulative, and we will kind of be hitting I'm counting on you knowing those. If you didn't know them for this test, you're going to want to kind of pick them up for the next units in here. So for 6, I was after either electrons, protons, neutrons, or a combination of to answer the question. So for A, which subatomic particle or particles allow the protons to coexist in the nucleus? That would be the other subatomic particle that's in the nucleus, the neutrons. Question B, which are positively charged? Protons. C, which are found in the nucleus. So you had to put 2 subatomic particles, the neutrons and the protons. For D, which determine what element an atom is? That would be the number of protons, the atomic number. Question E, which subatomic particle or particles weigh about 1 AMU? And the answer is the neutrons and the protons. Question F, which are most attractive to the positively charged protons? That would be the negatively charged electrons. G, which largely determine the mass of an atom, and that's actually kind of related to E up there, G and E. It would be your neutrons and your protons. H, which are most important in chemical bonding, that would be E electrons, which have no charge, that's the neutrons. And J, which subatomic particle or particles can an atom of the same element have different numbers are. And I was really after neutrons for the kind of the concept of an isotope, but if you put neutrons and electrons, I took it. Okay, so in this shorthand notation for Ag stands for, of course, silver. Here we have the mass number and the atomic number. And then we have some questions down here. So the mass number is 108. The atomic number is 47. So number of protons is also 47. Number of neutrons is gotten by difference. You take the mass number, protons and neutrons, and you subtract the protons. And you get 61 neutrons. And the number of electrons would be the same as the number of protons, since there's no symbol here in the upper right hand corner, so it must be neutral. So we have 47 protons, 47 electrons. And so here was, of these two, go ahead and tell me which one's larger, and go ahead and circle it. And since aluminum and chlorine are in the same period, size increases from right back to left again, so aluminum is larger. Potassium and sodium are in the same group, and going down the group it's larger, so that's potassium's larger. For C, actually bromine and tin are in two different periods and groups, but the going down the group, and I think it was actually both of them work in the right direction, so tin is larger. Okay, so number 9, the arrow diagram. And you could actually use this then to help you answer the questions down here. So for number 10, for phosphorus and magnesium, I wanted you to go ahead and show me how the electrons are configured using the box and arrow diagram. So good job, I would say in general. And I was looking for you to designate which subshell you mean these boxes, these orbitals to be in. So you can see the 15 electrons around phosphorus and the 12 electrons around magnesium. So on my answer key here for 11, each of these were 2 points apiece. I think it was hard to get partial credit here. You either got it or you didn't. And most of you got it. So I was after the electron configuration, and I've emphasized in my homework and lecture that I'm using according to the lowest n plus L rule. I was not looking for any exceptions to be applied. So anyway, bromine has 35 electrons. You could use the abbreviated rare gas notation beyond argon. Here are what the electrons do. Otherwise, you can write it out, and here's what I'm just going to kind of let you kind of ruminate over the answer key if you want to. To check them, kind of what I did was to see if you got kind of the end part of the configuration right, and if that was the case, you probably got the whole thing right. So let me know if you have any questions. All right, so these were each worth 1 point apiece, a little different than the example exam I gave you. But in this case, I've got you limited to carbon, nitrogen, neon, magnesium, sulfur, chlorine, potassium, nickel, silver, xenon, barium, lead, and uranium. And you have to tell me of these which fit the bill. And if none of them fit the bill, then you were supposed to say none. So a rare gas would have been any 8A element, neon and xenon. A transition element would be anything group B. So I got nickel and silver, and uranium. That'd be kind of an inner transition element, but that's okay. C, an element that has exactly 2 valence electrons. And the way this works then is it would be anything in 2A, or actually any of the transition elements. So probably magnesium and barium came to mind, but these actually, nickel, silver, and uranium also have 2 valence electrons. D was only one element. It has to be from the main group. Main group element has to be a metal. So magnesium only fits the bill. Now E, S block, you would have been looking for the 1A or 2A elements, so magnesium, potassium, or barium. For F, a nonmetal that has a valence shell electron configuration of NS2, NP2. So you're looking for a P block element, specifically the second column of p-block elements, which would be the 4A elements. And we want a non-metal, so it's got to be what, on the top of the JAG. So carbon and lead fit that. Is lead a non-metal? I'm not sure about that. Carbon, maybe. Gotta double check. G, an element that has a partially filled D subshell. So you're looking for a D block element, and nickel and silver fit that description. H, a non-metal found in period 5. Xenon is the only one that fits that bill. I, alkali metal, so that's, you're supposed to know the name of some groups, and group 1A is the alkali metals, so potassium. For J, an inner transition element, and that would be your lanthanide or actinide series, so uranium fits that bill. K, an element with exactly 8 electrons in its valence shell, so that would be your rare gases, your inert gases, your noble gases. 8A, we have 2, neon or xenon. L, an element that has a ground state electron configuration with 2 unpaired electrons. And the way that works is you could either go 4A or 6A. So that means carbon, lead, or sulfur. For M, a halogen, so that's 7A with a valence shell electron of N is equal to 3. So that is actually then in period 3. So chlorine fits that bill. For N, an element that will have at least 1 electron in the F-type subshell. So that, as it turns out, will be anything after atomic number 57. So lead and uranium fit that bill. So then on this last page, worth 4 points apiece, were the number problems. So for 13, how many moles of atoms, so moles is more important than atoms, how many moles are there in 3.149 grams of sodium? Well, we can get from grams to moles using the molar mass of sodium from the periodic table. So if we put the mass of sodium as our first term over 1, then we're going to use what the flipped version of the molar mass, 22.99 grams per 1 mole. So grams cancel, we left with units of moles, round to 4 significant figures, so 0.1370 moles of sodium. Question 14, what is the mass of 0.0795 moles of argon? So again, we can go from moles to grams using the molar mass of argon, which from the periodic table is 39.95 grams per mole. So if our first term is the moles that we want to convert, 0.0295 moles over 1, then we use the non-flipped version of the molar mass, 39.95 grams over 1 mole, so the moles cancel, we left with units of grams, and round to 3 significant figures because that's what we have here. This 0 is not significant in the 0.0295. So 1.18 grams of argon. For 15 now, it says what now is the total number of atoms? So we are going to have a big number, probably going to have to use Avogadro's number here, in this mass of carbon. We can go from grams of carbon to moles of carbon using carbon's molar mass, and then we can go from moles of carbon to carbon atoms using Avogadro's number. So here's the molar mass of carbon. Here's, the relationship for Avogadro's number and a mole. So down here, if we start with the 15, only 2 sig figs, 15 grams of carbon over 1, use the flipped version of the molar mass, 12.01 grams of carbon per 1 mole of carbon. Grams cancel, we have moles here. Now we use Avogadro's number of atoms, 6.022 times 10 to the 23rd carbon atoms over 1 mole. So moles cancel, we have carbon atoms. Round to only 2 sig figs, we got 7.5 times 10 to the 23rd carbon atoms, not to be confused with catoms. Get it? Carbon atoms, catoms. This last one down here was dealing with the element mercury. We have the density of mercury, 13.6 grams per milliliter. We're going to unpack that right here. And we're after volume. And the other thing we have is 1.15 moles of mercury. So the molar mass of mercury can get us then from moles to grams, and then the density of mercury can get us from grams to milliliters. So this is how this works down here. I have 1.55 moles of mercury that was given. That's my first term. If I go ahead and introduce the molar mass of mercury, use the non-flipped version, 200.5 grams of mercury over 1 mole of mercury. Moles of mercury cancel, we have grams of mercury. Then I go ahead and use density. Now I'm going to have to use the flipped version of density, 13.6 grams of mercury per 1 milliliter of mercury. So my grams will cancel. I have units of milliliters on top. It's all about the units. So rounding wise, it looks like 3 sig figs. Your answer should have been 22.9 milliliters of mercury. So don't hesitate to let me know if you have any questions. Like I said, this course does build, and so you're going to want to know this for down the road.